Good afternoon, everyone. How's everyone doing today? Excellent. Welcome to day 2 of our capstone presentations for space physics and astronomy here. Before we get going, I do want to send a general reminder announcement. Dr. Huey had told everyone via email, and I'm reminding you that the annual Space Physics and Astronomy Forum is on Friday from 2 to 3:30 in 57B. So please come there. There will be some snacks provided. It is your chance to talk to your professors about issues with curriculum, and new improvements can come of that. So we have new classes that are going into the experimental phase next year, in part because of what we've heard at the forum. Okay? So today we have 7 more of our graduating seniors that are about to embark on their journeys in their careers or grad school or whatever. And we are happy to have them present today. First up today is Ashlyn Primer, who's going to come up and give a fabulous talk called Tracking Neutron Backgrounds in the CCM. And she's been working with Dr. Smith.
Yeah, so like you said, I'm Ashlyn, and I've been working with Dr. Smith on tracking neutron backgrounds in the CCM detector at Los Alamos. So a little bit of background information. You can see in the left picture here, that's a diagram of what it looks like inside the building, and the right diagram describes what's happening inside of the detector. So the light dark matter, or neutrino, will run into an argon atom, and it will be either excited or ionized, and then that atom hits another argon atom, and it turns into argon-2, which usually can't happen, and it's not a very stable state. So then eventually it moves back to just 2 separate argon atoms, and in doing that, it emits a photon in the very ultraviolet, and that is not detectable by the photomultiplier tubes, so it gets wave shifted to just the ultraviolet, and then the 200 photomultiplier tubes that are inside of the detector can pick those up, multiply them, and then they're recorded as a pulse. So how neutrons come into play is that they produce gamma rays, which are also picked up by the photomultiplier tubes. And this diagram shows you how that happens. And this becomes an issue because they're picked up by the photomultiplier tubes the same way as the photons do. There's no way to distinguish the 2 interactions, and as the search for light dark matter and the sterile neutrino rely very heavily on how many interactions are detected, the neutrons can make a very big difference and affect that data. So what I did with this project was build a Monte Carlo simulation of 600 to 800 MeV neutrons going through the first section of shielding, which is 5 meters of steel. And the goal was to answer these questions. So we wanted to see if the neutrons would make it through that shielding in the same time window as the neutrinos or the light dark matter would, which is the 200 to 300 nanosecond window. And then if they would have enough energy to actually produce the gamma rays that would cause an issue. And so these are some of the plots that we made with the simulation. The one on the left is a normalized distribution of the scattering angles of neutrons. And we used that to sample a set of 116 angles, which is the number of interactions that we calculated to be how many interactions would happen in that, that set distance. And so we can, with that, find the ratio of the number of neutrons that are actually going to make it through the shielding. And then the figure on the right is a path of a neutron that we produced using the simulation. And as you can see, it kind of jumps all over the place. It doesn't go in a straight line the same way that a neutrino would. And the simulation is not quite accurate yet. We're hoping to finish that up in the next couple days. And we could answer these questions here. But if we don't finish it up, then it would be a great project for another student to continue probably next year. Questions?
Are there questions for Ashlyn today? Having a hard time seeing over the whites. All right, well, if there's no questions for Ashlyn, let's give her another round of applause. Our next presenter today has been so active in the department, she hardly needs an introduction. It's Janessa Sloan. Okay. I think that was picked up on the YouTube stream even without the mics. Janessa has done a lot for our department, especially with the SPS chapter, having even been an intern for the National Organization of Society of Physics Students. And today she's going to talk about what she's been working on with Dr. Bailey with new short-range tests of gravity and more.
Hello. Hi, everyone. Thank you, Dr. Richardson, for the introduction. Like you said, I have been working with Dr. Bailey for the past couple years, and I also worked with Jennifer James, who graduated last year. So the first project I worked on is new short-range tests of gravity, which is a theoretical physics project where our goal was to calculate the modifications to the Newtonian potential energy equation. And these modifications can be used by experimentalists around the world. There are various projects going on, which I'll talk about a little bit later. So basically, there are some theories that there are violations of general relativity and Newtonian gravity at very short distances. So we're looking at sub-millimeter distances. So we use the standard model extension, or the SME framework, which basically allows arbitrary Lorentz violations in our calculations. Like I said, there have been experiments worldwide that have been carried out that are using these modified equations to find any violations of Newtonian gravity. So my work began my sophomore year, where I started doing background problems using a first course in general relativity, which is the book that I am holding on your left. I took a photo with this book because it carried me through my research sophomore and junior year. So basically, I used it to understand complex concepts that we don't quite fully get into. Basically, until grad school is when you'll start looking at those a lot more. So it's like tensors, form momentum, curvature, things like that, which then led me into using the action principle with Lagrangian functions, where this equation is the Lagrangian density for the gravity sector. So without that last term in that equation, it's just general relativity, but that last term imposes a Lorentz violation. So what I did next was obtain the field equations from the Lagrange density for the gravity sector, which are here. So that first equation is the derived field equation in the linearized gravity limit, and then the second coupled equations are the field equations in the static limit, which then leads to Jennifer's research, who is my partner. So she was able to take H00 and HJJ, plug those in, and solve for the coefficients and the lambdas in terms of the coefficients K00 and K trace. So our new proposed solution takes the form of that first equation right there. So this is a very simplified version of the equation. We have the alpha 1, lambda 1, and alpha 2 and lambda 2. But you can compare that with the Yukawa potential. So you'll notice that we have 4 parameters rather than 2, including 2 length scales instead of 1. So lambda is our length scale, and alpha is the strength of the gravity. So this plot right here, the yellow and the green are the excluded regions where tests have been carried out and there has not been any violation thus far. but our goal would be to fill in the white and get closer to the bottom left corner. So like I said, experimentation has been carried out throughout the world, specifically at the Huazhong University of Science and Technology in China. So they have been mainly using the Yukawa potential that was on that last slide, and they have found no evidence of Lorentz violation thus far, basically meaning Einstein is correct so far. So we finished that project up, and we were able to publish a paper in January 2023. So I moved on and started working on the modified LV radiation with Dr. Bailey, which is basically studying the modifications to electromagnetic waves. So I found the radiation field for general E&M, which is that first equation right there. And then now I'm moving on to the modified E&M with Lorentz violations using the 4-vector potential A mu down there. So in summary, our goal was to study modification to the potential energy equation. We found the first exact solutions for short-range gravity tests in the SME framework, and experimenters can use these modified equations to carry out more experiments and get closer to that bottom left corner on that plot. And our paper was published in Classical and Quantum Gravity in January of 2023. Jennifer is at Vanderbilt University for her physics PhD, and I am actively applying for various jobs in STEM engagement, outreach, research, software development, coding, a bunch of stuff. I would like to thank Dr. Bailey for being my mentor these past couple years, my professor 3 times, and my colleague, and Jennifer James for being my friend, colleague, and for her dedication on this project, and the NASA Space Grant Consortium, Undergraduate Research Institute, and the National Science Foundation for funding me and supporting me. Thank you. If you have questions, please ask Dr. Bailey. I'm just kidding.
All right, what questions do we have for Janessa today? Dominique.
So this is some pretty cool research here. What implications or what's the results that you guys think that you might come out of this? What impact will it have on gravitational research?
That's a great question. So it's not going to have an effect on like our gravity today, right? So it's not going to have an effect on 9.8. It's not going to change gravity for us. It would basically just add to the findings of physics and add to the findings of what happens at submillimeter levels. So just things that we don't know right now.
We have other questions today? All right. Well, let's give Janessa another round of applause.
Thank you, guys. Good luck.
Next up today, we have Kenna Nagler, who's been working with Dr. Huey. She's going to give us a talk called the LIGO Detector Characterization ahead of the O4 Observing Run.
All right, thank you, Dr. Richardson. Good afternoon, everybody. Like you said, I'm Kenna Nagler, and I'll be talking about LIGO detector characterization ahead of the O4 observing run. So a little bit of background, as most of you know, LIGO is the Laser Interferometric Gravitational Wave Observatory, and they observe gravitational waves from compact binary coalescences, or CBCs. So LIGO is made up, their detectors, it's extremely sensitive, very, very sensitive. So while they're picking up those gravitational waves, they also tend to pick up extra noise that they don't want. And these glitches can sometimes mimic astrophysical signals, and they also just generally interfere with the gravitational wave data that researchers are actually trying to analyze. So this leads to detector characterization, which aims to identify those glitches and then splice or remove them out of the actual gravitational wave data so it's easier to analyze and it doesn't have all that extra. Known glitches are identified, and data quality flags are used to kind of identify them so that researchers can understand them better. And then this better understanding of glitches leads to an improvement in equipment and interferometers so they can get better data, as well as just being able to analyze the data more effectively because it's more simple and doesn't have those noise artifacts. From this general topic understanding, I did a few sub-projects. So I looked into thunderstorm glitches and whether or not they were consistent over time between 03 and pre-04 data, retraction events, and kind of how we can minimize those going into the 04 observing run, and then finally data quality shifts and what that's going to look like in the 04 observing run. So thunderstorm glitches are one example of external noise that interferes with gravitational wave data. So in this case, the auxiliary channel that's corroborating the glitch seen in the gravitational wave strain channel is a microphone. It picks up the thunder as the thunder rolls through during a storm, and that kind of shakes the detectors and causes a glitch that looks like this one up here on the left from 03. Now the goal of this project was just to determine whether or not thunder was creating the same types and shapes of glitches in 03 when it was first looked into and pre-04. So what I found was that it is very, very similar. So going into the 04 observing run, we can expect thunder to continue causing the same types of glitches, which is going to make it much easier for researchers to, again, be able to splice that out of the gravitational wave data. A retraction event is a publicly announced CBC candidate event that gets rescinded or retracted because there's an issue with the data quality that researchers found after it was announced. So obviously it's much better to identify these issues beforehand so that we don't have to retract CBC candidate events. So we looked into we just did a post hoc analysis of retraction events that have occurred in the past to determine what was causing those and how many of them could possibly be avoided in the future with better knowledge or foresight. And so what I found was that 38% of retraction events had matches to CBC and burst data quality flags, and another 8% of them matched gravity spy outputs, which are not data quality flags, but they just identify the morphologies specifically of glitches in the gravitational wave strain channel. And so we've got a nice plot there showing that there are quite a few that had issues that we can hopefully minimize in the future. So going into 04, that observing run, we can avoid so many attraction events by not announcing the ones that are known to have these data quality issues, which would be easiest if we have much better knowledge of what the data quality flags are before they're announced. And then finally, data quality shifts. So DQ shifts, as we call them, they help us understand the data quality issues in a given week of information coming in through LIGO's detectors. And we do this by looking at the summary pages, A-logs, H-veto, the band limiter root mean squared or BLERMS plots of seismic activity and noise to determine why there were lock losses. Were the lock losses caused by something? What's causing any kind of low frequency noise that we see? And so compared to 03 data quality shifts and the information available for that, the pre-04 data has relatively more lock losses and noise in general. And a lot of this is simply because the detectors aren't really up and running or fully operational in observing mode. So what we kind of got out of this is essentially that the infrastructure and setup that LIGO has for conducting data quality shifts is working. It works. We can look at it and get the information we need for the data quality shifts. But we're going to expect it to go a lot more smoothly and have a lot more to work with during the 04 observing run because they will actually be in observing mode instead of being down so often for maintenance and things like that. This concludes my presentation.
What questions do we have for Kenneth today?
Hi, Kenna. How does one announce a data quality flag?
So I went on their the public-facing website, and they just list, I think, when this CBC candidate event is expected to happen. Correct me if I'm wrong, Dr. Huey. But then if there's a data quality shift that they see if there's a data quality issue, that they see come up, they'll retract the event and basically then publicly unannounce it.
Megan, can you go ahead and set up? Well, we have one more question from the back row.
Yeah, you may not know the answer, Kenna, but it's something I often wonder about. If we didn't do any of this data quality stuff, right, and didn't worry about retractions or anything, how many, like what fraction of the events we would actually think were gravity waves would be data quality related?
That would be a better question for Dr. Healy.
Any other questions today? All right, well, let's give Kenna another round of applause. All right, next up today, we have Megan Piet, who's been working with me on, you changed the title compared to what's on the announcement, but that's okay. On dust properties of a Wolf-Rayet star that we observed with Sophia.
Thank you. Like Noel said, I'm Megan Piet, and yes, I've been doing research on WR137's dust properties with Sophia. So just what I'll be talking about today, quick introduction into Wolf-Rayet stars and what we ended up doing, a couple relevant figures, our result, a conclusion, and of course time for questions. So what are Wolf-Rayet stars? These are massive, highly evolved stars that have lost their outer hydrogen envelope. They have stellar winds of 1,000 kilometers per second, as well as a high mass loss rate. And there are two types. There's carbon-rich, WC, and nitrogen-rich, WN. And WCs in particular are prolific dust makers, and this is the spectral type in WR137. So Endo et al. In 2022 observed a 8-micron feature, and for WR125, a different dusty Wolf-Rayet binary system. And this is often associated with a 6.4 micron feature, which can't be observed from the ground due to a water feature in the line of sight. So we used Sophia, which is basically an observatory on a plane. And we were able to look above that water feature and collect some spectra, which is just the flux versus wavelength, to measure the equivalent width of the 6.4 micron feature as well as other known WR lines, and compare them to see if this feature is due to dust or if there's another reason it is occurring. So a couple figures that are relevant. On your left is a long-term light curve showing that as the dust is being produced, the system gets brighter in magnitude. And also the 3 spectra that we collected with Sophia, as well as a model showing a couple of the WR lines that we measured in comparison. And these were the results that we ended up getting. So this top plot is showing all of the equivalent widths. The colorful symbols are the known WR lines. As you see, as the continuum increases, these are actually decreasing in strength, while as the 6.4 micron, which is the black dot, is increasing. So we can conclude that this is in fact due to dust. And we also have the ratios that we took, and they all have a similar trend. They're all increasing. The only thing is that 5.8 micron feature is spiking up more. So there could be possible contribution from the dust here as well. So in conclusion, we used Sophia to look above that water feature and measure the equivalent width of 6.4 micron feature in comparison to some WR lines, and we were able to conclude that it is occurring due to dust. Thank you, and any questions?
All right, what questions do you have for Megan today? Your talk was that clear. Good job.
Thank you.
Let's thank Megan again. Come on, Ben. All right, next up we have Ben Nikolai. He has been working with Dr. Grutterson. And while he pulls up his talk, he is going to be talking about measuring birefringence uniformity in large area aluminum gallium arsenide crystalline mirror coatings. And I challenge anyone to say that 5 times fast.
Where's the present?
If you click that little button.
This one.
There.
Got it. Thank you.
That'll do it.
Hello. I'm Benjamin Nikolai. I've been working with my professor, Dr. Grutterson, and this is my talk about birefringence uniformity in aluminum gallium arsenide crystalline coatings for LIGO. So I should probably explain a little about LIGO because that's where this project sort of starts. As previously talked about in one of the other presentations by Kenna, it's the Laser Interferometer Gravitational Wave Observatory. They take a look at very far away massive objects that are either orbiting each other or combining that produce gravitational waves. Then they cross over this device called an interferometer. It slightly changes the arm lengths just a tiny bit, and the phase difference between the light in the arms causes a very noticeable change in the interference pattern after the beams recombine in the beam splitter, and this way you're able to detect gravitational waves. For our research, we're looking at mirror coatings, and the reason they're important is because LIGO is currently using amorphous coatings, and they're looking to upgrade to crystalline coatings for better thermal noise. Obviously, less noise is better data, usually. But they have one issue that these amorphous coatings don't have. Amorphous coatings are made out of this isotropic material, and they don't really care about the polarization of light when it comes to the speed of the light in the medium. However, crystalline coatings do have a sort of directionality component to the crystalline structure, so it gives rise to this effect called birefringence, where the speed of the light inside the medium changes based on the polarity of the light, so that's why they care about this. Basically, you can have this effect that adds up over many reflections, say in a cavity where light is bouncing back and forth between mirrors, and you can potentially remove this systematically or design your experiment such that this isn't an issue, but you need to be relatively certain that the birefringence uniformity is, well, uniform across the surface of the mirror. So that's why this is important. This is basically what I spent most of my time on. These are repurposed secondhand XY stages that we used to drive around the samples. There wasn't any proprietary software that came with these. I had to basically write the software from the ground up. The only thing I didn't end up writing was the drivers, thankfully. In LabVIEW, there's all sorts of issues, for example, stuff like missing a checksum modulo operator. So checksum is just something that validates the operation for the servo. And without this modulo operator, instruction size would be too big, wouldn't move around. So I was in charge of debugging all of that goodness, as well as doing the actual data acquisition and making sure we're within the physical constraints. You can see on the left, there's not a lot of room because these optics tables aren't terribly big. This is just our simplified optics chain for the experiment. We have a laser with vertically polarized light, and that goes through a quarter wave plate. Then it moves to our sample, reflects off our sample, goes to a beam splitter, and that's split off into 2 photodiodes. And if we measure difference between the 2 photodiodes, then we expect that to be due to birefringence. So pretty simple. This is some very early data we took. On the left here, you can see the amorphous gold coating. It's relatively uniform, although it's a little bit noisy, and it's relatively close to 0. That's about what we would expect, because we don't expect a birefringent reading for the gold material. Unfortunately for the aluminum gallium arsenide coating on the right here, you can see that there's this large massive gradient over the whole surface, and that's not what we want to see. We would hope to see a uniform birefringence reading, but fortunately this is not birefringent effect. It is actually imperfections of the sample. Due to the manufacturing process, the sample is slightly bowed. There might be a few milliradians of difference across the entire surface of the coating on the sample, but this is enough to move the laser off our photodiode, so we can't measure birefringence with these samples. We need something a little bit flatter. So that's what we have here. This is very recent data, I think maybe a few weeks ago. On one side of this coating is the amorphous coating they use in LIGO, and on the other side is the aluminum gallium arsenide coating. And you can see that they're relatively uniform across each side, but there are different values, which is what we would expect because one is amorphous and doesn't have birefringence, and we expect the other side to have birefringence, so that's nice. But unfortunately, you probably can't see it due to the resolution here. There's still a lot of noise and like horizontal lines, which we suspect there to be like beam power wand over the many hours this scanning experiment takes place. So we need to either reduce the noise, remove the line systematically, this error, or upgrade our hardware, but that can be prohibitively expensive. So that might be like a future thing. On the other side, on the right, this is just transmittivity. You can see these diagonal line structures through the algas coating. We think that might be like parasitic interference, either in the coating itself or in the substrate the coating is laid upon. So this might be something to worry about as well. And then other future stuff might be like applying a heat gradient to the sample and looking how the birefringence uniformity changes as we strain the sample a little bit. But yeah, that's about it. Any questions?
Thank you, Benjamin. Are there questions for him today?
I was just curious, on the first slide, you had something called an input mode cleaner, I think was the name of the part. I was just wondering what exactly that does.
I'll be honest, I don't particularly understand this exact diagram in its entirety. This is just like some example interferometer. This is not something we learned in optics, so I wouldn't be able to tell you exactly what it does. Yeah, sorry.
It does what it says it does. It cleans the mode of the light coming in, makes it a more pure Gaussian laser beam.
There you go. That was Dr. Gutterson for you.
All right, well, let's thank Ben again. Next up, we have Hayden West, who's been working with Dr. Smith. And he is going to give us a talk exploring neutron interactions in a liquid uranium engine.
All right. Thank you, Dr. Richardson. So today I'll be talking to you guys about the project that I've been working on with Dr. Smith for the last 2 semesters that's called Centrifugal Nuclear Thermal Rocketry. But first, before we get into that, and I like to pretend to be an engineer, what exactly are we going to talk about? Well, what is CNTR? What did I set out to accomplish? And what did I actually learn? And what did I actually accomplish? So first off, what is CNTR? Well, as I kind of already explained a little bit, CNTR is Centrifugal Nuclear Thermal Rocketry, or Centrifugal Nuclear Thermal Propulsion. So CNTP or CNTR. This area of research was very recently restarted, somewhere around 5 years ago, with the earliest papers being in the early 70s when they were doing the NERVA program, which was the solid rocket version. And as such, there are very, very, very few research papers on this subject, and the research team itself has actually only produced a couple of papers in recent years. On top of this, the engine, like I've stated a few times already, is using liquid uranium as its fuel element. So the uranium in the engine heats the propellant to a very high temperature of around 5,000 Kelvin on the inside of the engine, and that is kind of what produces your thrust. I'll talk a little more about that later. We also have something called a CFE, which is these little circular doodads here in the picture in the top right there. Centrifugal fuel elements, because these things spin in order to keep the uranium in. And we use a porous medium to push the propellant through into the liquid uranium. And from here, it superheats to 5,000 Kelvin, and it gets pushed out the back as propulsion. So, good question is, where is CNTR now if it's only been in research for around 5 years now? So right now, the big area of focus is actually bubble physics, which is extremely complicated, and I will not be getting into that today. They've also done steady state models for when the rocket is firing, for the actual neutron stuff as well as heating. They've also done little to no knowledge on liquid uranium properties, which is another area that they're looking into. They also built a total full functioning version of one of these cylinders that you can see, and they have a larger research group now. To kind of explain these graphs here on the right from the other research papers, the nice looking color plot there is actually the neutron flux inside of the reactor. So the top one there is the fast neutron flux. So that's neutrons moving too fast to provide thermal power. And then the one on the bottom is neutrons moving slow enough to provide thermal power. And then on the right here, you can see temperature graph on top, where you can see that it actually goes up to 5,000 Kelvin on the inside of the engine. So that kind of moves us into what did I set out to accomplish? Well, so I created this very nice looking diagram to help out. So the main bit that I was focusing on here was actually doing the neutron or neutronic study, which is the center line here, and that is primarily what I focused on. This was kind of an overall focus for the project, as we were looking to study what was going to happen when we introduced different propellants. Unfortunately, as you'll find out, I only got to that first blue box there called use tallies to create distribution profile, and that's about it. So that leads us to the next point. What did I actually accomplish? Well, so I was able to accomplish building actual physical geometry in Python, utilizing a library called OpenMC, or Open Monte Carlo, that was produced by MIT to model nuclear reactors. And so here you can actually see on the left is actually my model for, so this is like a cross section on the far left. The middle is a XY cross section to actually see all the different elements. And then on the right here, I have the good distribution of what all of the actual innards on the inside of these centrifugal spinning fuel elements look like, and the different and the actual different materials that make that up. But the next slide is a little more fun, because if you see here on the picture behind me on the left-hand side, there is, I have a 3D model here of all the different neutrons moving about in the medium of the reactor, as well as an actual 3D cross-section of the actual reactor itself. Just to go through some quick, interesting color maps that I was able to produce, you can see here on the top that I was able to produce a total neutron flux event color map that kind of shows where all the neutrons and photons were interacting inside of the reactor, as well as the probability energy distribution for fission events here on the right. I also got a K effect, which is essentially how many neutrons are going in and out of the reactor of 1.22, which means the reactor is very active and could melt. And of course, we have some absorption and elastic cross-section color maps over there that basically show that that's where all the neutrons are being absorbed. In conclusion, of course, I did not quite complete everything that I was looking to set out to do. As these color maps kind of indicate, we should be seeing this, but we're not. So in the color maps on the right there, you should be seeing a 1-to-1, but we're not. I suspect this has to do with the fact that I did not integrate multi-group cross-sections for the neutrons, and so that's one of the big reasons why this didn't work the way it should have. But for future development, I've placed all of my code on GitHub for everybody else to use, to modify and to change, so that way the project can continue. And also, my big thing, of course, is maybe defining the elements a little bit better. And that concludes my presentation. Any questions?
Thank you, Hayden. It looks like we have at least one or two questions.
Maybe
I'll
three.
start with students.
So my question would be more on the K effect. You said it was a 1.22. How would you basically reduce that value itself?
Yeah, so the K effect, you should be seeing a K effect of about 1.05 or so. because you want it to be a little above 1 so the reactor can sustain itself. So to explain a little more, K effect is the ratio of fission events to loss of neutrons. So you want to have more fission events than loss of neutrons. And so having a really high K effect is a little bad. To reduce it, what I need to do is change my materials a little bit, because I think I misdefined some of my materials, which is why I had such a high K effect.
Quick question. I don't know much about this form of propulsion, but it looks like you have one particular different method of nuclear thermal propulsion from other ones. Does this one is supposed to have some advantage over those? What?
Yes. So some of the more recent papers actually have put this at having an efficiency in terms of ISP of around 4 times that of chemical rockets or twice that of solid nuclear thermal propulsion, which is the typical. And then you also have, then it also produces around 50,000 newtons of thrust. Some have been putting it at, so that's why it's pretty useful.
Question for Hayden.
Hi. So with this form of propulsion, how practical is it? Because it seems like you have to keep that uranium hot and liquid. So how do you plan on doing that, or how would that be feasible?
Yeah, so one thing that we can kind of start looking into as the project progresses is something I started finding out was that actually at a very low temperature, it seems to be supercritical with that 1.22 K effect. So it could actually start off solid and then melt itself for a starting method. I don't know about shutdown, but there's definitely an easy starting method.
All right. Thank you again, Hayden. That brings us to our final capstone presentation today. Last but not least is Justin Carpenter, who has been working with Dr. Jones on gravito-optics and intensity correlations for transient signal detections.
Awesome. Thank you, Dr. Richardson. Hey, I'm Justin, obviously. I've been working with Dr. Jones the past little over a year now on gravito-optics and intensity correlations for transient signal detections. So first I want to talk about HANBURY, Brown, and TWISS interferometers. And so that's going to kind of go over LIGO again. And then the second order Glauber correlation functions, which is what we used to look at the intensity correlations. And then we'll talk briefly about the optical equivalency theorem. So this map is a kind of a demonstration of the 2 LIGO detectors. You can imagine the gravitational wave propagating across the map from red to blue, and then the intensity is picked up by the detectors. And so we're going to look at the correlations in that time lag between those detectors. So obviously if the gravitational wave was propagating and hit both at once, they would overlay perfectly, and if it comes across perpendicular to that, then you would get the farthest in tau value. So the second order Glauber correlation functions are as shown. And so the wave functions are in integrals, like its bottom is shown here. The problem is with this is that it uses t as a period. And so these are the first and second order Glauber correlation functions, with tau being that time lag between the 2 LIGO detectors. So we want to use intensely weighted functions. This has already been done with traditionally weighted functions using the period, and so because there's not a well-defined period for gravitational waves, we want to use intensity weighted functions. And so this work was done by a previous student, Alex, and he derived these equations. And so as you can see, the intensity functions in the Glauber correlation functions weight the function, and so we're going to see that in a minute when we look at the graph that was produced. So something that we used was a toy model. So we're looking at compact binary coalescence. And so if we look at this graph on the left here, there are 3 different phases. The first phase is the in-spiral phase. That's in red. Then there's the merger phase in black. That doesn't last for very long. And then the ring down phase in blue. And so using that and these second order Glauber correlation functions, we can produce the graph on the right. And so this is the correlation between the LIGO detections of the compact binary coalescence. And so you can see as the that tau value, so the time difference between the detections is very small, you can get a peak where the correlation is a lot great, and then if it's much farther apart, then tau is obviously larger, and then the correlation is much less. So if we look at something in the future, maybe the space-based detectors, then we can actually have much, much greater tau values. So the optical equivalency theorem is interesting because what we really want to look at is the graviton, and because the graviton is a boson like the photon, you'd think, oh, it's super easy to just form a theory of quantum gravito-optics like quantum optics, but it's not so easy because the graviton is so difficult to detect. And so what we're doing with this graph is actually forming a better theory for quantum gravito-optics using HANBURY, Brown, and TWISS interferometry. And so because one of the problems, again, is this optical equivalency theorem that says that classical and quantum processes can be indistinguishable without a good idea of the actual theory behind what's going on. And so this is one of the challenges we're running into, and so more theory and papers will be published, hopefully expanding this theory and allowing us to have a better, more defined theory for the graviton. I'd like to thank again Dr. Jones for helping me, and also URI for helping this become possible for me. Some of the sources were used. So.
All right, are there any questions for Justin? Everyone's tired. Guess you're off the hook.
Not that exciting, I guess. I thought it was.
Anyway, as a reminder, again, we have our Space Physics and Astronomy Forum Friday at 2 in Building 57B. Please come. There will be snacks. We want you to take all the snacks and give us feedback on stuff. Let's thank all of our seniors again. And I forgot to do this yesterday, but if all the seniors could come up for a group photo, including ones that presented yesterday, if you're around, that would be great. I'm sorry I forgot yesterday, but let's try to get at least one shot while we can. And I hope everyone has a great rest of your day, and good luck with your final exams.